Okay, so we'll do the same thing with another graph, but in this graph, what I want to add on to the graph is some what you call weights for the nodes in this graph. So it's a different graph. It's a graph of 7 vertices. I could give you some weights for the nodes. That could be, say, for example, in a social network, the ages of people or anything like the height, whatever. So here I'm giving just fraction of numbers. It could be any nature of integers. It could be like whole integers indicating the ages of the people and so on. Now, as you noticed in the algorithm that we just went through, we considered only the edges. So if I want to run the same algorithm on this graph with some some node weights, we'll not be still considering those node weights as part of a procedure for finding the maximal node matching. And we'll do like that and find out some set of edges that are part of a maximal node matching. Now we will try to then find out what is called this assortativity index for just these three edges, or whatever the set of edges that we find for the maximal node matching, and check if those three edges or those edges are a part of the maximal node matching or assortative or not. Okay, so let's do this. So again, given this graph, we want to find the maximal node matching, and for that we have to simply discard the node weights. We're not going to be considering it. So apply the same procedure that like we did in the previous example. Find the coverage weights for the edges just by considering the edges. So for node 1, for edge 1, 3, its coverage weight is the degree of node 1 plus the degree of node 3 minus 2. So the degree of node 1 is 1, the degree of node 3 is 4. So 1 plus 4 minus 2 is 3. For edge 2, 3, the degree of node 2 is 2, the degree of node 3 is 4, so 2 plus 4 minus 2 is 4. For edge, say, 5, 6, the degree of 5 is 3, the degree of 6 is 4, so 3 plus 4 minus 2 is 5. That's the coverage weight. So once you find the coverage weights of all the edges, remove the edge or pick the edge with the smallest coverage weight. That's going to be 3 in this case, corresponding to edge 1, 3. So remove the edge 1, 3 and put it in the set of edges for the maximal node matching, as well as discard or don't consider its adjacent edges anymore, which are going to be 2, 3, 3, 4 and 3, 6. Those three edges are removed also. So on the remaining graph, calculate or update the coverage weights of the edges depending on the edges that are left over. So for 2, 4, its coverage is going to be the degree of 2 plus the degree of 4 minus 2. So it's going to be 1 plus 4, which is 5, minus 2, that is 3. That's the coverage rate of 2, 4 and so on. So now again pick the edge with the smallest coverage weight. That's going to be 2, 4. So its three adjacent edges 4, 5, 4, 7, 4, 6 will be gone, and these are the remaining edges, each with coverage weight 2. So for example, for edge 5, 6 is degree of 5 is 2, degree of 6 is also 2, so 2 plus 2 minus 2 is 2. So if you have a tie, you can break them in any fashion. Let us say I break in favor of 5, 6. So these are the three edges that are picked up. Now once you pick those three edges, so that's called the maximal node matching, and here you have 7 vertices, and you have found a maximal node matching of 6 vertices. And I said like earlier, if you have odd number of vertices, the best you can do is v over 2 minus 1. So if you have 7 vertices, you have matched 6 of them. So the maximal node matching has 3 pairs of edges, and that's why this maximal node matching is also a maximum matching. Okay, because it's the best we could do of the number of vertices that could be matched. So it is 6 over 7, that's the percentage of node matches, that is 86%, and that itself is the maximum matching for this graph because it has odd number of vertices. So now what we want to find out is whether the end vertices of these edges that we selected for maximal node matching, Are they similar to each other with respect to those node weights that were also given in the graph? Because we did not consider them for finding the maximal node matching. But now let us see if the set of edges that we picked up for maximal node matching have similar values for those node weights. So we can write down those edges and the node weights. So 1, 3, 2, 4 and 5, 6 are the 3 edges that we picked up, and the corresponding node weights are this. So again we can follow the convention of xy. So here I call uv. So u is the you write the edges in this order, the lower id first followed by the higher id. So 1, 3, 2, 4 and 5, 6. So for node 1 its weight is 0.5, that's given to us in the graph. Node 3 its weight is 0.9. Node 2 is 0.7, 0.3 for node 4 and so on. Now just by looking at the numbers, we are going to go through the math, but if you just look at the numbers, we can see it is 0.5 and to 0, and this is 0.9, this is 0.7 and this is 0.3, 0.1 and 0.8. They are not really close to each other, especially the last one, 0.1 and 0.8. So you can think that the node weights on a scale of 0 to 1 in this graph, they are not really very close to each other. So your hypothesis or your guess, initial guess, is going to be that the calculations are going to lead to a negative value for the assortativity index. And yes, it is coming out to be negative. Okay. So that indicates that the end vertices of the edges that are part of the maximal node matching that we pick for the graph are not assortative or more dissortative in nature. Dissortative means they have different values for they are different from each other on the basis of the node weights. So let us go through the calculations now. We went through it earlier today and last class also. So the first step is to find the average of, so now we are not doing with node degree, we are just doing with this node weights given on this graph. So find the average of these values, which is 0.5, 0.7 plus 0.1 divided by 3. That's going to be 1.3 divided by 3, so 0.43 is the average. I'm not sure whether that's the right number. Yeah, 0.43. Okay. Then the average of these three numbers, 0.9 plus 0.3 plus 0.8 divided by 3 is 0.67. So as I said, the average need not be the same, and here it's not the same. Now take the difference, u minus average of u. So 0.5 minus 0.43 is 0.07. 0.7 minus 0.43 is 0.27. 0.1 minus 0.43 is negative 0.57. I think this is where there's a mistake in this calculations. Okay, negative 0.33. So this should be negative 0.33. Somehow messed up. Okay. So let us go with negative 0.57. It's not going to make a big difference. It should be negative 0.33 because it's 0.1 minus 0.43. I'll update the numbers after the class. Okay. Similarly, find V minus average of V. So 0.9 minus 0.67 is 0.23. 0.3 minus 0.67 is negative 0.37. Now let me see, one second, I have some other set of slides in which I should have the updated numbers. Still the same thing. Okay. Updated it somewhere else. Alright, so let us go with just this negative 0.57, and it should not be much different if it's negative 0.33. Alright, so V minus average of V is 0.9 minus 0.67, that is 0.23. 0.3 minus 0.67 is negative 0.37. and 0.8 minus 0.67 is 0.13. And then what you do is find the squares of these numbers. So 0.07 square is this, 0.27 square is this, negative 0.57 square is this. Similarly, squares of these numbers. And then also take the product of these differences. 0.07 times 0.23 is this. 0.27 times negative 0.37 is this. Negative 0.57 times 0.13 is this. So why we do all these things? If you look at the formula for assortativity index, which I also gave you earlier, it is the sum of the product of the differences in the numerator divided by the square root of the sum of the squares of the differences and for both x and y. So in this case u and v. So that's why we are doing this. So you find the sum of the product of the differences, negative 0.1579, that's going to be the numerator, and then find the sum of the squares of these differences. So sum of the squares of u differences is 0.4027. Sum of the squares of the differences on the basis of v is 0.2067. Take a square root of each of them and multiply in the denominator. So if you go through the calculations, in this case it comes to be negative 0.55. So that indicates the network is kind of not the network, the three edges that we pick. Okay, the end vertices have dissimilar edge weights. Dissimilar means they don't have similar edge weights. So it's not like 0.5 and 0.6 for the edge 1, 3, and it's not like 0.1 and 0.2, or not 0.7 and 0.8 for the edge 5, 6. So two edge weights of the end vertices should be similar or close to each other. So here they are not close to each other that much. So we get the assortative index to be negative. So given a graph with node weights, you should be able to go through the algorithm to find the maximal node matching, as well as go through this set of calculations to find the assortativity index or assortative index. Okay. Any question on this? Right, so let me see if we need to say we have time, we can both continue. Alright, so now what I want to find is, so we found out that if you totally discard the node weights and just go based on the edges, the coverage weights of the edges, we are able to find maximal node matching. But since we totally discarded the node weights as part of our algorithm for finding a maximal node matching, we found in this example that we may end up picking edges whose end vertices are not similar or having dissimilar node weights. Okay. Now, what if our objective is to pick edges as part of a matching such that the end vertices of those edges are very similar to each other? So the similarity of the end vertices is the primary objective now, and the secondary objective is to maximize the number of nodes that we pick. Okay, and if you want to do that, the matching is going to be called the maximal assortative matching. Okay, so if you want to pick a matching or set of edges such that the end vertices that we pick as part of the matching should have similar weights or should be similar to each other. That's the primary objective. And the secondary objective is to maximize the number of edges we pick in such a set of edges. Okay, that's called a maximal assortative matching. And a maximal dissortative matching is, again, pick the set of edges such that the end vertices are as different from each other as possible. And among such set of edges, we want to find a maximal matching, the set with the more edges, as many edges as possible. So the objective for maximal node matching that we did earlier is only to maximize the set of edges that we pick, and we don't really consider the node weights. Okay, So that was the picking the set with the maximum number of edges is our primary and only objective. As here there are two objectives, and the primary objective is to pick edges with similar node weights, and then the secondary is to maximize such a set. So that means we have to consider two things. Okay, so to pick edges, to pick the set with the maximum number of edges that we did for maximal node matching, we use this notion of coverage weight, right? And we picked the edge with the smallest coverage weight and went ahead with the algorithm. So we will retain that as part of now the procedure to find this maximal assortative or maximal dissortative matching. But we also want to take care of what? The primary objective of making the end vertices of the edges that we pick similar to each other. So what we'll do is we'll find the absolute value of the differences in the weights of the end vertices of the edges. So we'll take the same example here where the node weights can be in the range of 0 to 1. Okay. So in general, the node weights need to be on the same scale. Okay. So if you look at the ages or height or whatever, it should be on a comparable scale. So because otherwise the calculations would not be accurate. Okay. So the ages of people, they cannot be too different. If one node is having age 10, some other node cannot have an age of 1000 or something like that. That's not reasonable. So the ages should be on a reasonable scale. Similarly, the height of people and so on. Of course, they are the reality. In reality, what ages we can observe. In reality, what height we can observe for people. Okay, then they are not automatically comparable to each other. Okay, so here let us assume the node weights on a scale of 0 to 1, and these are the node weights we have. So what we'll do is we'll find a tuple for each edge. So previously we found just the coverage weight for each edge and went ahead with the calculations. Now for each edge we'll find a tuple that has two entries. The first entry is the coverage weight of that edge by just considering the degrees of the end vertices, and the second entry is the absolute value of the difference in the node weights. So for this H13, its coverage weight is 3 because it's the degree of 1 plus the degree of 3 minus 2. So 1 plus 4 minus 2 is 3. And the absolute difference in the node weights is 0.5 minus 0.9 or 0.9 minus 0.5. Either way, the absolute difference means take only the positive value of the difference is 0.4. So that's the tuple. And once we find the tuple or the two entries in the tuple, take the product of those two entries. So it's 3 times 0.4, that is 1.2. Okay, so that's a kind of combined weight for this edge. Do the same thing for every edge. For 2, 4, the coverage weight based on the degree is 5 because it is 2 plus 5 minus 2, so it is 5. And the absolute value of difference is 0.7 minus 0.3 is 0.4. So 5 times 0.4 is 2. That's the kind of combined weight. So do such calculations for the given graph. And now again what we want to do, we want to find this maximal assortative matching. Means we want to minimize the differences in the node weights of the end vertices we pick, as well as maximize the number of edges that we pick. So that means in the maximal node matching case, we preferred edges with a smaller coverage weight, right? And we want to minimize the differences. That means the second value in the tuple should also be smaller. So we prefer a smaller value for the first entry and a smaller value for the second entry. So the product needs to be also smaller. Okay, so among all the different weights we have found now for the edges, we pick the edge with the smallest value for the product weight, the combined weight, and the smallest among the different numbers you have 1.2, 0.6, 0.82, 4.2, 4.2 is going to be 0.6. So that's the edge we pick, 3.6. Again, it's the product that we look for the minimum. The individual values need not be absolutely the global minimum. Okay, so once we find the product of the two entries, we'll focus only on the product. And again, as I said, it's a greedy approach. It's not guaranteed always to have a global minimum solution. So once we pick that 0.6, the corresponding edge 3,6, that's the first edge that is part of our maximal assortative matching. And we automatically discard those 6 adjacent edges, which are these 6 adjacent edges from being considered. So these are the remaining edges that are there in the graph, and these are their coverage weight and absolute difference in the matching. And again, absolute difference in matching comes from the original weight, absolute difference in the node weights. Then the coverage weight comes based on the degree of the updated graph. So for node edge 2, 4, it is 1 plus 3 minus 2, so it is 2, and 2 times 0.4 is 0.8. So among these 4 edges, 0.3 is the minimum in the product. So we pick this edge 4, 7, and once we pick the edge 4, 7, automatically these 3 adjacent edges will get ruled out. So these are the 2 edges that we can find for a maximal assortative matching, 3, 6 and 4, 7. And you can check right away manually that their node weights are very close, 0.8 and 0.9 and 0.3 minus and 0.4. So that's what I said. So that's our primary objective of finding this matching. We want to find a set of edges that are very close to each other. Now, is it a maximal node matching? The answer is no, because for the same graph of 7 vertices, we found a maximal node matching that can cover 6 of the 7 vertices. Whereas here we covered only 4 of the 7 vertices because there are only 2 edges. So the percentage of nodes matched is going to be 4 divided by 7, that is 57%, less than 86%. Now let us go ahead with the calculations for assortative index and see what is the assortative index for these 2 edges that we have picked for the matching. So 3, 6 and 4, 7 are the 2 edges, and we write down the corresponding node weights. So weights of node 3 and 4 are 0.9 and 0.3, for 6 and 7 is 0.8 and 0.4. Find the average of these numbers, average of these numbers. So 0.9 and 0.3 average is 0.6, 0.8 and 0.4 the average is also 0.6, just coincidence. Okay, then u minus average of u, 0.9 minus 0.6 is negative, 0.3, 0.3 minus 0.6 is negative 0.3. Do the same thing here, 0.8 minus 0.6, 0.2, 0.4 minus 0.6 is negative 0.2. So once you have the differences, take the square of the differences. So 0.3 square is 0.09, negative 0.3 square is 0.09. Do the same thing, square of these differences, 0.2 square, negative 0.2 square. Sum those squares and take the product of these differences too. So 0.3 times 0.2 is 0.06. Negative 0.3 times negative 0.2 is 0.06. Then the sum of the product of the differences is in the numerator, and the square root of the sum of the squares is, and the product of these two is in the denominator. And if you go through the math, you will get 1 as your assortative index. So, and I said for assortative index, it can be anywhere from negative 1 to 1. If you get 1 or closer to 1, or typically positive values greater than 0.2, you can claim the edges that we consider are assortative in nature. So here we see that they are very close to each other. Okay, now that's what we mean by assortative. So the edges that we pick should have similar values for the node weights that we consider. Now if you want dissimilar values for the node weights, the same process, but we want the difference between the node weights to be as much as possible. So find the tuple as I just explained earlier, the coverage weight and the absolute value of the differences of the node weights. Take the product of the two entries, and instead of picking the one with the smallest value for the product, pick the one with the largest value for the product. So it comes out to be 4.2 in this case, and that's the edge we pick, 3, 4. So when we pick that edge, it's 7 adjacent edges are getting ruled out. So these are 3 edges that are remaining, and these are the entries for the coverage weight and the absolute difference in the node weights, and the largest among this is 1.4. So we pick now this edge 5, 6. Now just by looking at the numbers for the node weight, you see the node weights for the end vertices are reasonably far away from each other, 0.3 and 0.9, 0.1 and 0.8. And we can check that in the, through the calculations for assortative weight. Again, go through the same process, write down the edges and the node weights, find the average of the U and V entries, 0.9, 0.1, the average 0.5, 0.3, 0.8, the average is 0.55, then find the difference between the individual entries and the average, and then squares of the differences, product of the differences, sum all these things. So the assortative index is the sum of the product of the differences in the numerator, and square root of the sum of the squares of the differences in the denominator. Take the product of those two, and you get -1 as the assortative index, and that's the best we can do for dissimilarity among the edges. Whereas the percentage of nodes matched, we have matched only 4 of the 7 edges, so that is close to be 4 over 7, 57%, and that's not a maximal node matching, because for same graph we came up with a maximal node matching earlier with 6 out of 7 vertices matched. Okay, so you can see a trade-off between the percentage of nodes matched and the assortative index. In the first case, when we targeted maximal node matching, we were able to find maximal node matching, or which is a maximum matching, 6 out of 7, but the assortative index based on the given weights was like negative. So the graph, the matching ended up to be dissortative in nature. So if we really wanted assortative matching, we could not find that in this graph by just finding a maximal node matching. So if you want really a maximal assortative matching for this graph, we have to go through this process of maximal assortative matching and find a set of edges. But then on this graph we see a trade-off. We could not really find a maximum matching. We can just find a matching of just 57% of the nodes matched, but that is the best. That's assortative in nature with a one assortative index. Similarly, if you want to find an assortative index close to -1, we can do a maximal dissortative matching process by picking the edge with the largest of the product of the entries in the tuple, and that will lead us to -1 for the assortative index of the edges that we pick. But again, that's not the maximum matching. We have only 57% of the nodes matched. Okay, so sometimes depends on the graph. There could be a trade-off like this. Sometimes we could find a maximal node matching itself to be more assortative in nature. Like this one is kind of more dissortative in nature. So if you're satisfied with this, differences 0.5, 0.9, reasonably large differences, we can go with this maximal node matching and claim that this is also dissortative matching. But if we really want something very close to -1, we have to go through the process of maximal dissortative matching. Okay. Alright, so any questions? So it's probably time for a break. So let me save this video.